All right, step one is to analyze the function. Okay, so what I mean by that is, one of the things that we have to do is what? Symmetry. Does this have any symmetry? What happens if you plug in f at negative x? It's going to equal to, because of the x to the power of 4, exactly f at x. This is an even function. This is fantastic. Okay, as soon as you realize it's even function, this is what we're going to do. I'm only going to find out how it looks from 0 and on, and I'm just going to draw a mirror image on the other side. Okay? Alright. What about y-intercept? You set x equal to 0 and you get ln of 27. Okay, which is same as 3 times ln of 3, because 27 is 3 to the power of 3. That's not really important. Okay, we're gonna punch down the calculator anyways. Okay, so that's 3.3 approximately. Accurate to 1 decimal. X-intercept is when y is equal to 0. So we have ln of x to the power of 4 plus 27 is equal to 0. This is the same thing as x to the power of 4 plus 27 is equal to e to the power of 0, which is 1. Okay? So then we get x to the power of 4 is equal to minus 26. This is impossible. No solution. That means it's not touching the x-axis, this graph. Okay, that's kind of cool, right? So that's actually nice. We don't have to worry about the x-intercepts. Step 2. Analyze the derivative now. Okay, differentiate that, you get this. 1 over chain by the derivative inside, which is 4x cubed. Alright. Do you see that this is going to be positive or equal to 0 when x is greater than or equal to 0? This is actually very nice. Right? The bottom is always positive because it's x to the power of 4 plus 27. So the entire thing is going to be positive when x is positive. The entire thing is going to be 0 when x is 0. That was actually very simple. Second derivative. This is going to get a little bit messier. Differentiate the x cubed, 3x squared. Quotient rule carefully. Right. So I hope by now you're good with your derivatives. If you're not, the chance of you finishing this question is very low. Okay. Alright, let's clean this up. You get 3x to the power of 5 or 6, 81 x squared minus 4x to the power of 6. Okay, let's combine these two. Okay, and then you get 81x squared minus x to the power of 6. Okay, let's factor out what we can, which is x squared. And you get 81 minus x to the power of 4. Okay, here, do you see this is the difference of squares? This is going to be 9 minus x squared. Right? 81 is 9 squared. This is x squared squared. So it's 9 minus x squared and 9 plus x squared. This can be factored one more time. Alright, so this is the final form. We're going to analyze this. So if you set that equal to 0, the potential inflection points are 0 plus minus 3. Anything from here?
That's already there. No, wait, no.
This cannot be 0 because it's x squared, right? So these are the potential inflection points. Okay, to determine it is an inflection point, I need to know when this is positive and when it's negative. Okay. Now, let's do some analysis here. This one here, this one here, and this one here is always positive, except this one can be 0. Does that make sense? So the whole thing will be always positive as long as that's positive, right? The problem becomes just figuring out when is that positive. Then I know the entire thing, when the entire thing is positive. Okay. So when is 3 minus x and 3 plus x positive? Okay, I'm just going to multiply this one in by -1. So you get x minus 3 or x plus 3. Because, and I have to multiply the -1 to the other side as well. Okay? And you get -0. So whatever x values that satisfy this condition will make the second derivative positive. Now this is an easy parabola. So when x is in between -3 and 3, the function is concaving up, or the second derivative is positive. Alright, so I'm gonna organize all of this information. It's kind of hard to see, whoa, what just happened? The first derivative, now I have a second derivative, like where does how does it all fit? So how do you make it all fit is the box, okay? The box that we introduced. The box involves x, okay? The first derivative, the second derivative information, and the function information. Okay. Now I'm only going to draw from 0. Remember, because it's an even function, from 0 all the way down. Okay. So normally you have to draw the entire interval, but because it's even, only from 0. So what are the critical numbers that we have to worry about? 3. And what about up here? What about from the first derivative? Only 0, right? Well, that's actually very simple. 3. Yeah, it's turning very simple, right? So I know that the first derivative is positive where? Let's go back. It's positive as long as x was positive, right? So this is all positive. Where was the second derivative positive? Only here, right? In between the -3 and 3. So it'll be negative there. Okay? Of course, it's equal to 0 there. So this means it's doing this. It's going up and concaving up. So it's doing that. And here, it's going up, but it's concaving down. So it looks like that. So this is an inflection point. So we need to find out what this value is. So in the original function, it was ln of, what was it, x? What was it? X.
It's x4 plus 27.
Wow. So we gotta plug in the calculator. 3 to the power of 4 plus 27. Okay, this is 4.7. Okay, 4.7. Now, when x was equal to 0, we actually had the y-intercept. It was, what was it? 3.3. Okay. 3.3. Okay, so remember, it's not touching the x-axis, right? So it's got to be purely above the x-axis. Now here's, let's say 3.3, and let's say, you know, that's 3.3. Let's say, you know what? Let's make the 3.3 a little bit higher. Let's say that's 3.3, and 4.7 will be about there. 4.7. So this is the y-intercept. And 0, 3. So let's say about 3. Right there, it's 4.7. And it's doing this. Okay? It's doing this. Okay, concaving up and then concaving down. And it's got to do that symmetrically on both sides because it's an even function. Okay, that's the graph.